Naples because he spent 2 years there after doing a undergrad in physics and a PhD in physics at URGS. He went to spend 2 years in Italy, and now he does very good pizza, Napolitan pizza. And he also does some physics in the free time, you know, when he's not cooking pizza. Okay, so that's what he's presenting now today, I hope.
Thanks, Carolina. Now? Okay. So it's a great pleasure to be invited to this school by Carolina and Danilo. Andrea is not important for what I'm going to talk. Because many years ago, we organized a school in Bento Gonçalves, almost 20 years ago. And probably I'll ask a question that will have more answers than your last question. How many people here were in that conference? Leticia, Carolina, Ezequiel, Danilo, Leticia, that was in the previous week, was also a student there. So I believe that school was a great success because now we have students there that are organizing new schools. And so in the future, you have to organize something and invite them to give seminars in the school. Okay. So what I'm going to talk today is related with Leticia's lecture yesterday and today. And I will be the one that will show a lot of images and figures, and I probably won't write anything in the blackboard. Okay, so I'll give a brief introduction to phase ordering and percolation, in which is the connection between them in the Ising model, I don't know how to call the guy. And we apply this in out of equilibrium situations, and there are many recent experimental results. That's the main point of my talk, is to show these new results, quite new, last week. And so this is I'll explain later the details, but just to give an idea of what are the systems involved. This is an experimental imaging. This is what Leticia was mentioning this morning. If you take or this is very hard to, yeah.
I can help you do that.
No, I can't. So if you take an horizontal line, this line will cross different domains. The colors, just pay attention in the green and black colors. The orange one it could be black as well. So if you take an horizontal line, that line will cross very many domains. And that was the line that Leticia was showing today. The domains were just a cut, an horizontal cut in one of the possible directions in this image. So here you can see two different times. So this is mostly in the beginning and at a later time. And you see that many of the small domains, they disappeared. And the orange one is the largest cluster in this image. You see that it became fatter. Okay, it has less holes. Okay, so it evolves in time, and the evolution that we are interested. Okay, so this is the main picture. And okay. So to give some background in this subject, you probably know about percolation, but I know that many of the Brazilians, they don't know the word percolator. They know the cafeteira. Okay, but this is a percolator. So when we study diffusion, we have a simple medium and a particle that makes the stochastic process a walk in this simple medium. In percolation, we have the opposite. We have a stochastic medium. This is an example of a granular system. So depending on how you prepare your coffee to put in the machine, the water will pass through with more or less easy, and that depends on the quality of you gonna get with this coffee. Okay, so when the water that you put in one of the interfaces goes out in the other interface, then we say it percolated. It went through the whole system. Okay, so this is one example of percolation. This is this simple model that we can build to study it. And this is a square lattice where we put a fraction with a given probability P, and then we get a fraction of occupied sites. All these blue points were chosen independently. So there are no correlations between the places where we put particles. In black, we have the largest cluster. And you see that by increasing the probability, there is a geometric transition where we have a percolating cluster, a cluster that goes from one side to the other or from top to bottom. Okay, and this is around 60% of occupation. This cluster has many interesting properties. For example, it is a fractal. You can see that it has a lot of convolution. The surface is very convoluted. It has a lot of holes. Okay, so its mass that is given by the number of sites, it doesn't increase with the square of the system size. It increases with a number that is slightly smaller than 2. Okay, this is its fractal dimension. Okay, and this critical point, the transition that we have here, this is a signature of this transition. If you measure the distribution of sizes that you see. Okay, here we are not counting the largest cluster, but all these smaller ones. This distribution is given by a power law that has its own exponent, the Fisher exponent, and this one. Okay, these are signatures of this transition. This will be important when we describe later the out of equilibrium behavior of the Ising model. Yes. L is
a perimeter of the cluster, or is the diameter?
Neither. L is the length of the side of your lattice, the system linear size.
And M is the largest cluster mass.
And M is the number of black points in this image, or in this image. Okay, so it's the mass of the cluster given in sites, number of sites.
Ah, got it. Okay.
So if yes, this relation, it only becomes a fractal at the critical density. Okay, the critical probability. For example, if you take a small cluster, it's compact. So it's the number of sites that you have here grows at the radius to 2, to the square. So it's a non-fractal object. Okay, and we'll find some of these signatures later when we study the Ising model. Okay. So just to give a more quantitative signature of this transition, this is the size diversity or size heterogeneity is a quantity that gives us information about the number of different sizes that we have in a configuration. So if I take this single configuration, and so this is the distribution of sizes after we average over many samples. But if you take just one sample and measure this distribution, we'll have some clusters that appear in that distribution. There will be some sizes that are lacking. Perhaps we don't have, for that configuration, we don't have any cluster with 77 sites. Okay, so you don't have. And I just count the number of sizes that are present in that configuration. And that quantity I average. This is this age. Okay? And you can see that as this is for increasing system size, increasing L's, this quantity has a peak because for very small p, you have a lot of small clusters. Let's go back here. If you take a small value of p, you have many, many clusters. All of them are small, and probably they are very similar. So there are a lot of clusters with size 1, a lot of size 2. There are no large clusters. Okay, so the sizes are not very diverse, and this age will be small in this size. In the other size, there is a probability 1 that you have a giant cluster that occupies most of the space. And the remaining space, you can find a few clusters. Okay, this may be different, but there are just a few. And then the diversity will be small again. It's only close to the transition when the distribution becomes power law, very broad, that you have some larger probability of having different clusters, a few clusters of each size, okay? And then you have a peak, and this peak is a good indication of the location of the transition. Just to give you a more quantitative and simple signature of the transition in this case. And then this is the guy. This picture is interesting because he's spinning a wheel. So that's why people, everybody uses this picture. So Ising, he was German, so I think it's Ising. Ising, he studied his model in one dimension. He didn't find any transition, and then he became a teacher, a high school teacher. Okay? Very disappointed because of a lack of transitions in his model. Okay, but in this model that Leticia also explained yesterday, we have spins, two states spins that if the temperature is low enough, they like to be parallel. They try to align with the neighbors. And there is a critical temperature. Because if you study the system in contact with a thermal bath, okay, there will be some amount of noise that avoids these spins, that inhibits this process of becoming parallel, okay? So if the noise is too high, they cannot organize themselves. If it's low, we can have a state with order in the system. Otherwise, at high temperature, it is disordered. I was asked to use at least once the word disorder in the seminar to justify, because I'm by the bad copy here. Okay. So this is the model where we'll try to find signatures of percolation. Some of these are very well known. You probably studied how close to the critical temperature percolation is important in the Ising model. So in 2 dimensions, if you define a cluster by a connected set of parallel spins, so in white we have down spins, in black we have up spins, and all of these blobs, if they are connected, if it's possible to walk from side to side of each of these blobs, they form a cluster, a domain, okay? There are different definitions, I'll mention it later. But if you just use this simple definition, if we, at very high temperatures, the noise destroy all the organization that they have. All clusters are small. And if you decrease the temperature, it's at the critical temperature where there is a percolation transition in this model as well, okay? So the thermal and geometric transition, they are connected in equilibrium in the system. Not with this definition, but with a slightly different definition of cluster. It's possible to make a parallel between the critical exponents in percolation and the thermal exponents, critical exponents in the thermal transition in this model. This connection between percolation and phase transitions has been used to define cluster algorithms that optimize simulations in many spin models. So there is a huge literature and applications of percolation concepts, geometric concepts in equilibrium spin models, in the equilibrium easing model. And we can also measure this distribution of size. It's a power law at the critical temperature with a different exponent, okay? Just to have a comparison with the percolation, this is a related measure of the size diversity. We can see that there is a peak very close to the critical temperature, and it becomes closer the larger the system is, okay? So I won't mention, I don't have time to discuss what is called the physical cluster, but these are the two definitions, possible definitions of domains of clusters that I will use in the remaining of the seminar. So this is the cluster that I defined earlier. It's a connected set of parallel spins. You obviously may have holes with spins in the opposite direction. So they are not part of the cluster. They are not parallel. And if I considered only the external perimeter, what is called the hull, I can define a different domain by counting all the spins that are inside this perimeter, even if there are some small domains inside, okay? So these are the two measures that I will discuss. But, okay, okay, this is just a summary, I'll skip. So the question now is, okay, in equilibrium, it's well understood. What happens if I take my system out of equilibrium, okay? And we'll see that geometry becomes also an important concept. So what I mean by that? Leticia already explained it. I will explain again with figures, okay? Just, so the temperature quench is the following. I take my spin configuration at infinite temperature. How I do that? I just choose the spins by chance. 50% probability of being up and 50% of being up. So there are no correlations between these choices. They are completely independent. And this is how I simulate an infinite temperature. And then I make a temperature quench. So when I introduce a dynamics, the metropolis, for example, dynamics in this model, instead of evolve the system at that temperature, I will jump to 0 temperature, and then I will evolve, okay? So noise is very high here, and all clusters are small. This is the largest cluster, This is the second largest cluster, very, very, very small. Of course, there are no correlations between the spins, but by chance I may have a large cluster just by coincidence. Okay, and then I evolve the system and see what happens. So because the temperature is small, the energy all spins try to become parallel. And these domains, they will increase in size initially, okay? The average size will increase. The domains, we'll see that they will decrease in size. How it is possible, I will explain later. And these are some examples of the, very hard to do that in the blackboard, Leticia. You take the whole day to, okay. So this is a few steps after the beginning. We can already see that the largest cluster, I use periodic boundary conditions. This is, that's why the cluster, the part of it here and other part here, okay? The second largest. And as time goes on, we see that there is a transition, a percolation transition. This is not the time, but close to the time where at first there is a cluster that goes from one side to the other, okay? Later I will discuss that this is a little bit more complicated, okay? But you see that there is a percolating cluster in all of these figures, and the cluster, it still has holes, but the small clusters, they disappear. And if I wait a little bit more, this cluster will take control of the system. The magnetization will be 1 or -1, I don't know, okay? I'll come back to this picture later, because there is a very important thing here that you certainly didn't notice, but I'll show you later. So what happens in these systems? This is an example of an initial state that was prepared with a circular domain. And if you follow the simulation, you see that because of the Allen-Kahn law that Leticia mentioned today, there is this interface. It has a velocity that goes inwards, okay? It decreases in size. And if you take a lot of samples and you average, you see that this decrease is linear in time. Okay, this is what's written here. And this is, okay, you may say that, okay, if you take a very particular initial state, you have this simple law, but if I start with a random domain, okay, a domain that I take from a simulation, and I measure, I'll get the same thing, because it doesn't depend on the initial shape of the domain. So it's possible to show that the rate at which the area of any domain decreases in time, okay, if anyone is interested, I can come back to this later, but it's possible to show, because of the Gauss-Bonnet theorem, that this is independent of the initial, the rate is independent of the shape or the initial area of these domains. And by integrating this, you get these results. So this is very unexpected, because in the images, you see that the domains are increasing. The average, if you average the size of these domains, at the end you have a very large domain. It is increasing in time. So they increase in time by decreasing in time. Okay, why? Because all of the small domains, they are shrinking, and they will disappear. So the average increases because the small domains are going out of the system. We only keep the large guys, and then the average does increase. Okay? Okay, this is a very important result. This is one of the ingredients that will be necessary to, I have to go much faster than this. Okay, this is the second ingredient. This was something that we noticed in a paper that is almost 20 years ago with Leticia. So this is the size distribution of the domains that I observe after the quench. So these points here is, this is the distribution at the infinite temperature, okay? And is not a straight line, okay? But you notice that just a few steps, these are Monte Carlo steps, okay? So this is in the early beginning of the very beginning of the simulation, you see that the distribution becomes a power law, okay? And this power law, it's the same power law, it's the same size distribution that we get at the critical point of the percolation problem. Only there is this factor of 2 here, because in the percolation problem, I just have particles. In the spin model, I have up spins and down spins. So in the percolation water is just empty space. In the easy model is occupied by domains. Okay.
Jeferson,
so
is that two Monte Carlo steps?
This
the time 2 is only 2 Monte Carlo steps. So you swept through the
just twice.
Through all the spins only twice.
Yes. And then, so it's,
and that is the change that you observe.
So the point is, after the quench, it approaches the critical point of percolation in the first steps of the dynamics. And that was very unexpected, okay? And just this observation, there are many consequences that Daniel.
Yeah. This is for the whole, right? You count the entire thing. If you take the distribution of the masses.
Okay. Why I'm using the areas inside the holes? Because for this definition of domains, there is a very simple calculation that will give exactly the size, the expression of the size distribution. If I use the geometric domains, not counting the internal clusters, this is not exact. It's very similar, but the exponent is not 2, and we can get more or less to the same result, but with some approximations. So it's simpler to keep all the area inside the holes, because the demonstration is exact and very, very, very simple. Okay? So these two observations, the fact that all domains will decrease in size following the same law, the same linear law, and the second ingredient that in the very beginning of the simulation, I know the distribution of sizes, okay? And it is given by the same distribution that was exactly calculated in this century. It's not that old, okay? By Cardi and Ziff. This is a constant, okay, it's here. It's exactly known, okay?
It's interesting, there's a factor of 2 exactly between the two formulas.
I was trying to explain earlier. This factor of 2 is just because in the spin model, I have twice the number of domains, okay? Because I also count the down spins and Okay, so I just have double the number of.
Sorry, Jeff, when you say size distribution, percolation threshold, you're just putting particles with a given
No.
size?
So
That's as if, I'm asking about the
yes.
calculation.
So this is the distribution that we had here. The distribution, if you take configurations at the threshold, percolation threshold, just placing particles at random, and you
Particle here, you mean the sites? No, there are no
yes,
particles there.
yes, you can. Yes, you take a site and you say this site is occupied. Okay, with that probability, and then you measure all the size you have and you average, and you get the distribution, and this distribution is exactly known and given by this. And you see that the easy model after the quench approaches this distribution. So what seems at this point is that after the quench, we start at infinite temperature, but the system is attracted by the critical point of percolation. Okay? So I will wait longer then, okay? And what happens, this distribution will keep evolving because you have coarsening, but it will keep this power law tail, and we can, because of this initial information, we can evaluate the distribution and how it depends on time, okay? So I found this remark in a recent paper by Cardi, and he said, there the result that he is saying is this distribution for percolation would have sat gathering dust as yet another curiosity had it not been ingeniously applied in a series of papers by Cecilia, a former student of Leticia, and in what seems a priori to be a very different arena, that of non-equilibrium statistical physics. So this is the distribution of sizes for all times that we obtain with that two ingredients. The fact that all domains decrease in time by this linear law, and the fact that we know not the distribution at time 0, but if we consider the initial time around here, the time, so if you keep counting time after we have the power law, the percolation power law, we can consider this distribution as the initial distribution, okay? So because all clusters, all domains decrease in time by the same law, if you know the distribution at time 0, this distribution will just move as a wall in time, okay? You just take what at time 0 had this area, at a time t, will decrease this factor, and this is just A, okay? So by knowing the distribution at time 0, I know the distribution at all times. So I just put this here, and I have the distribution. This is exact, okay? Once you accept this, there are no approximations involved here. Okay, so we can simulate the system. There are one more thing. It's interesting that the lambda that we see here, we can use 2, because we get from this. And it's with the error bars that we have, it's 2. Okay. So if we make some simulations and go to later times, as you asked, and this line, the dots are the distributions at different times, and the lines correspond to these expressions without any fitting parameter. And you see that the agreement is really good, okay? And more importantly is by using this expression, you can, by applying the dynamical scaling hypothesis for the moment, I can rescale all these points here by using, Leticia explained this this morning, that if you take all length scales and divide by square root of t, you get some universal behavior. This is the area, so it's the square of a length scale. Then I divide by t. So you have a very good collapse, more than 8 decades. So this collapse is better than yours. So what we get with this equation is the demonstration that, yes. Because this is, you just interrupted me in the middle of the phrase where I was going to.
Sorry about that.
So dynamical scaling was a hypothesis because people used to do these collapses. And here, because we can demonstrate this equation, you see that you can put it in this form. And this is the demonstration that dynamical scaling is acting in this case, at least for this quantity. Okay, this is not a demonstration that all collapses that you get will hold this collapse, but at least here we can demonstrate that you get, by obtaining an universal function, a scaling function here, you see that the area goes with time, and of course the radius goes with square root of time. Okay, so this is the first consequence that we observed from the fact that the coarsening dynamics in the Ising model approaches the critical point of the random percolation. Okay, and then we can check that experimentally. So this is a molecule of this liquid crystal, and because of this, what they call banana shape it has, when there is an electric field, all these molecules try to align. In Portuguese is ficar de conchinha. Okay, sorry for the. You can sleep like a spoon? Okay. I don't know. Okay, and because of the chirality of these molecules, in some regions of the system, they align like this, and in other regions, they align like that, and these regions will have different optical properties. And if you put a polarizer, so you turn the electric field, and you observe these different optical regions, and what you notice is that it seems very similar to what we saw in the simulation of the Ising model. So this is a good candidate for test this. This experiment has a very interesting history, because Cecilia, that was the former student of Leticia, that he went to England to make these experiments. And this experiment seems to be very difficult because the sample is very hard to do. Okay, so the guys there send us a small set of images, and they said, okay, that was very similar. Alberto went there to make many averages and samples, and the first thing that he did was break the sample. Okay, and now he's a journalist in Ukraine. I don't know if there is a correlation between these two.
Jefferson.
So he left physics and he's in Ukraine right
Jefferson. That's a three-dimensional system, I suppose, right?
It can be considered a two-dimensional because it's very small in this dimension compared with the. Essentially,
Just a few.
I can look in the paper, but I don't remember. But it's very small compared with the other dimensions, and then you can consider as two dimensions.
Okay. Okay.
Okay. And then we measure the distribution of size with very bad statistics because of the limited number of samples. You notice that there is a granulosity in the images, and then there is this excess of small clusters. But by rescaling the area by essentially time, we get a very good collapse, and the line is that equation without any fitting parameter. Okay, so this is an experimental test of this, the first experimental test of our results. And then there is the second candidate to be in the same universality, dynamic universality class. This is the usual LCD that you have in the calculators. And, so this is a twisted nematic liquid crystal where the molecules of the material, they like to have some angle between them. And once you put some light through this polarizer, because of the organization of the molecules, you have a rotation here, and then you see the light. You have this rotation of the plane of polarization, and then you have light going through. But if instead of having this alignment between the molecules, you put a voltage here and you align them, you don't have this light, and you have you have dark regions and bright regions. If you prepare the system with a combination of these two regions, is very similar to what we have in the other liquid crystal. This is this is a paper by Renan Almeida that he spent some time. He did his PhD in Japan doing these experiments, and then he went to Porto Alegre with all his results. Okay, and there will be a second paper that I'll mention later. Okay, so these images, they look the same. So this is a second candidate. The only difference that Renan didn't break the samples, and he has a very good statistics. And this was published 2 years ago by him in PRL. And the lines, again, are this prediction. And again, we see that it agrees very well with the theory. So now we have two different systems and the Ising model. We have three systems showing the same behavior. So we have very good universality. Okay, okay, but these are the recent results. This was, that was Friday. Okay. One of his images, it was chosen to be the cover of the magazine. So what we try to do now is, okay, we have some evidences that the critical point that after the quantity system goes is the percolation critical point. But we decided that we should look closer to see whether that cluster that appears in the beginning of the simulation, if it has the same properties of the critical percolation cluster. Okay, so I'll come back to this image because I want to show you something that is very important. So if you take the largest cluster, the dark cluster here, okay, you see that the smaller clusters that are inside are red. Okay, so remember, black is the largest, white is the second largest, but red and blue are the orientation of the spins. Okay, so because of this clusters here are red, it means that the largest cluster is blue, okay? Just because I cannot have the same color in neighboring clusters. But if I go to this snapshot that is very close to the 0 time, the black cluster, the neighbor, the holes, the small clusters, they are blue. So the largest cluster in this configuration is red. The largest cluster in this and the other configurations are blue. Okay. So this is not the same cluster. This cluster, this black cluster and this, they have different magnetizations. So what happens is the following. It's true that early in the dynamics, there is the formation of this percolating cluster, but it's not stable. It keeps breaking and forming different percolating clusters. So there is a first time TP1, where it first appears a percolating cluster, and then it stabilizes at a later time. So this was observed in a paper by Laetitia and Blanchard and others. So if you take the largest cluster with up spins and the largest, or the second largest in the whole group, or the largest with down spins, you see that they keep changing. If you take the same time, they keep switching positions until a given time where the green one will dominate and occupy the whole system. The dashed line is the size of the percolating cluster. So the largest and the second largest keep fighting to see which one will win this run. At around here, one of them, perhaps both of them percolate, but they keep switching positions. So from here, this is TP1, the first percolating cluster appears. And in this window, they keep switching places, okay? So the phenomenology is a little bit more complicated than I will skip this one. So this is simulations that in the easing model. These are similar to simulations that Laetitia Blanchard they did, just the difference that we start earlier here, and then this is the size of the largest cluster, okay? So in the beginning of the simulation, all clusters are small. The inclination here is the dimension of the clusters. In the beginning of the simulation, the clusters are small, are round, are compact, and so the exponent is 2. At very large times, there are just large clusters. They don't have many holes. They are, once again, compact. But in between, they are fractal. And this is the fractal dimension of the percolating cluster, the cluster that you have in that simple model where you just put particles at random. So what this is showing is after you, so this is something interesting, that even the first percolating clusters, it seems that they already have the same fractal dimension that you have after they stabilize. So in this whole window of time, they seem to have the same fractal dimension, okay? So from the simulation, it seems that the cluster that we have in the easing model, once it percolates, corresponds to the percolation, the cluster that you see in the critical percolation. And then you can measure that in the experiments. And because of some technical problems, it was not possible to start the measures early in the simulation. So we cannot get the initial clusters. Only this is only after TP. Okay, I will show you later why. So again, this is consistent with the image that we had before. You have exponent, it's consistent with the exponent 2 here, with this fractal exponent in the beginning. It's interesting to put everything together, the simulations and the experimental data. They are very close, so it seems that the scaling function is universal. Okay, there are some difference, but there are some difference between the experiments and the simulations. For example, the boundary conditions are different, so that may be the explanation for this small difference. Okay, I'll just show very briefly some of the results. There are other results that you can get in all the papers that our papers that I mentioned. You can get in my web page. Okay. So this is a recent result that you get for the following quantity. You ask which is the probability of having a cluster that connects this point in the middle of the circle and a point in its border. Okay, so the black cluster is here, and here again there is a black cluster, but it's not in all of the places. Then you can measure for different radius, for different along the circle. You can put this point in different places. You can make an average. Okay, and for percolation, this is a theorem. And how this probability depends on the radius of this circle, is given by this relation with this particular exponent. So remember, we're trying to check whether the cluster that we observe in the experiment, if it has the same properties as the critical cluster in percolation. This is another property. And so here, this is the simulation. It agrees very well, but we are interested in the measurements. Okay, so I won't have time to explain, but it's possible to transform this expression for percolation. There is no time in percolation, but there is a length scale here, and if we use dynamical scaling, you can replace all length scales by the square root of time, and then we can check whether the observations either in the Ising model or in the experiments, if they obey this scaling, and we see that is very consistent with this exponent. And to conclude, a final measure. So this is the widening angle is if you take the border of the, I said I won't, but okay. And you take the vector that is tangent here and see how this angle fluctuates as it goes along the border. If you have a circle, there are no fluctuations, it's very smooth. But if you take one of those clusters in the beginning, this will fluctuate a lot, and this is a measure of these fluctuations. And there is a theoretical prediction. I don't have time to that says that the dispersion around the average goes with this logarithmic of this is the distance along the border here. Okay, so these are simulations by. Oh, I didn't put the reference, but there's a paper by Letizia, Marco Pico, other people. Okay, and these are the experiments. So the point here is that there are different systems that correspond to different values of this kappa, and for random percolation, it should be 6. In the simulation, it's very close to 6, and in the experiments also. Okay, so it's a different quantity. So these liquid crystals, either this twisted liquid crystal or the other one, they are very good systems in which all these geometric properties can be tested not only in simulations, okay? Now we have an experimental system, not just to test our results, but where we can discover new things. So this is a new window that it's opened. So just to conclude, just refer, you probably know Dr. Malcolm, and percolation finds a way, if you know what I mean. So it's thank you. For those that don't, that's Jurassic Park. The first one, where life finds a way, percolation finds a way, there is a double sense, okay.
Very, very beautiful results.
Thank you.
I was wondering, can you comment on the confidence about, you know the Fisher exponent is very close to 2.
Yes.
And you have a crossover between 2 and 91/48, so if I remember right, something like that. About the confidence of those measurements for the exponents. That's
so for the wholes, the exponent is 2. If you try to replicate this for geometric domains, where the exponent is the Fisher exponents, you cannot use this the same argument. You must go to some approximations, and then okay, the exponent will be. There is a dependence on the Fisher exponent. So the question is, how can I detect the difference between
2
that?
and 91/48. Yeah. I would suppose that be. You showed that collapse, right?
Yes.
Well, it's very subtle.
So if you, I don't remember, but probably we did that many years ago. But because we have 10 orders of 10 decades here, even if you take an exponent that is close, you'll see the difference in this.
Yeah. One of the last collapses that you had.
In the experiments, I mean?
Yeah, go ahead. A little bit more. There. Yeah.
Okay.
That's what. Yeah.
So this is real life. It's very difficult. You can, for example, measure the local derivative, but even if the statistics is good, I cannot say that this is. That's why when I mentioned, I said consistent with. Okay. But yes. It's the set of evidences that is convincing.
Yeah. No, thanks.
The measurement of the winding angle is the one that is really very precise, because it's this slope that depends on kappa.
Yeah, they change a lot.
They change a lot. From one universality class to another, it changes a lot. So there you are sure it's percolation.
Yes.
So, what is the quenching temperature that you do in the experiments?
In the experiments, actually, they are done at constant temperature. They use the electric field. The electric field is the surrogate for the temperature. You control. In both experiments, you use the field as the quenches, and you turn the field on. Okay.
So, another question, quick.
I don't understand much. If the
the
question is about the
details.
experiment,
No, it's not.
It's Renan, the guy.
Suppose that you take as the criterion for defining clusters, not the site percolation problem, but the bond percolation problem. Okay? You define that you have a bond. If neighboring spins are the same, you define that you have a bond, and you study the bone percolation problem. Then at infinite temperature, you are precisely on top of the percolation threshold.
You can do better. You can keep the side percolation and do that on the triangular lattice.
Okay, it's the same.
It's the same.
It's the same.
Okay, so what happens there? Okay, if you at time 0 you already have a percolating cluster, but it's unstable. It will break,
Okay.
and then later it will. But the point is, most of these percolation results, for example, in this one, this demonstration was for the square lattice. Or no, sorry, for the no, this one. This was a demonstration only for the triangular lattice. But we assume that there is some universality and it doesn't depend on the details of the lattice.
Just I have a question, because you showed us 2 experiments and in both you have the same phenomenology.
Yeah, they are in the same.
Okay, but my question is, this is a particular parameter that you change in experiment, for example, the electric field, which brings the system to
I don't
critical
know.
phase?
In those examples.
Okay, but can you have a phase where it does not happen in the experiment?
I don't know.
Okay. Okay, so the coffee break is ready. Everybody did sign the list? I don't know where the list is. Okay, so see you in the coffee break, and the day today is over. Thanks, Jefferson.
Thank you.